Hello everyone. The first video will be in discrete Fourier transform, and the second video will be some of its application in signals and system analysis. Now, discrete Fourier transform is a mathematical operation that will take a sequence of numbers. This sequence came from signals picked up by a sensors, like audio signals picked up by a microphone, or it could be signals produced in the human body and picked up by ECG, electrocardiogram, or it could be signals coming from the galaxy and picked up by a radar. Also, these signals can come from a mechanical system, vibration of a car or machines. These signals also can come from business, such as the performance of the Dow Jones, the stock market, every minute or every day. So basically, you have a sequence of numbers, and this sequence may be of size n. That could be 100 or 1,000 data point. And now you take it to a discrete Fourier transform. So I'm going to represent it by this box, discrete Fourier transform. And this mathematical operation will give you another sequence of data. And let's call it x of k. And this could be, it gives you back another sequence of data of the same size n. So if the signal here in the time domain of size 1000 data point, it gives you another 1000 data point. But this signal now is in the frequency domain. This number, for example, the 3, that will tell you the DC or the average of these data points. 3 plus J2, a complex number, that will tell you if there is a sinusoidal present in this signal of specific frequency, and the strength of this sinusoidal will be the magnitude of this complex number, and the delay or the phase shift of this sinusoidal will be the angle of this complex number. And this will be the second harmonic and third harmonics. So for discrete Fourier transform, it's pure math. It takes numbers and give you a set of numbers. Now, as engineer, physicist, biologist, or business, you have to interpret this data point and this data point, so you can make decisions. One of the big application of discrete Fourier transform, for example, in audio signal, you may have audio signals for like 1 second and you have 1,000,000 data point or 100,000 data point. You can find the frequency content, which is maybe 100,000 data point again. But maybe the first 100 data point is important, very strong. All the other frequency components are very weak. So you can eliminate them, filter them out, and then reconstruct the signal back again, and it will come almost the same as the original. And they use this in transmission of audio signal over the phone, internet, and so forth. Also, discrete Fourier transform, you can design a system that will filter certain frequencies and allow certain frequency to pass. And they use this a lot in artificial intelligence. They use it in detection. Also, they use it in understanding the nature of the signal. For example, this signal may come from the ECG, and you may find a sinusoidal in it that indicate the heartbeat, but you may see also a very sinusoidal with high frequency. That may indicate there is a muscles in the heart that beat or vibrate irregularly. So now I will get x of k here by carrying out this mathematical operation. X of n here, that is the data points in the time domain, or it could be in a spatial domain if it was an image or video. X of k here are the frequency content that are present in this signal. In this equation, the variable is n. So it goes from 0 to n minus 1. Omega 0 is the fundamental frequency of these data points. When k is 0, that will be the DC. So if I want to find the DC, k0, I plug for k0, and basically you just sum all x of n. If I want to find the first harmonic, That means k is 1. I plug for k1 and carry out all the sum, which is basically you multiply this signal x of n by a sinusoidal of frequency omega 0 n. So basically you multiply it by this and you sum. If this signal is present in this data point, you will get a large number. Then when k is 2, I want to find the second harmonic. Then again, you multiply x of n, which is this signal, by a second harmonic, which looks like this. So higher frequency. And if you multiply all this data point by this data point and you got large number, this will be very large. The second harmonic indicate this signal is present. If this signal is not present here, then when you carry out this, you will get 0, indicating this signal is not there. And that's what's the discrete Fourier transform. And we will explain it in more detail in the coming slides. Now, before we explain the discrete Fourier transform, it's very important to know how did we get these data points from a continuous signal. Usually signals in real life are continuous. They are not discrete like this. They may look like this. How do we convert this continuous signal to a discrete signal? It's very important to know it so you can make sense of what this data point means. So let me move here and explain that. So your sensors may pick up a continuous signal that looks something like this. So the first step after the sensors pick up this signal, you have to take samples of these signals if we want to process it using digital equipment. So the first step is you determine how many samples per second do you need to take. And according to the sampling theorem, the sampling rate f of s has to be equal or larger than twice the bandwidth or twice the highest frequency in the signal. So we have to go by this law. So aliasing will not be a problem in our analysis. And I have video that explains sampling theorem. So after we decide what's the sampling rate f of s, so we will take these samples. The next step is, as this signal is coming to your system, are you going to wait until the signal finish coming to your system, then you process it, you find the discrete Fourier transform and do all kinds of filtering? Or are you going to wait maybe up to this point and start processing these and transmit, then pick up the next segment of the signal? That's a decision you have to make, and it will depend on the application you are doing. For example, in telephone, hearing aid, cochlear implant, the process has to be in real time. That means as I'm speaking in the phone, I want my friend in the other side to hear me as I'm speaking. I don't want to have delay between my conversation and when he hear me. So when we talk, we are on the same page. If I take this to be 1 second, and this we usually call it the interval or the window, then there will be a delay. So as I'm speaking for 1 second, he is waiting, then he starts hearing, then I'm already talking and he's responding to my information that was 1 second earlier. So to avoid this lagging in audio processing, usually they make this T0 equals 50 millisecond. Now the impact of this choice will determine what is the fundamental frequency of the signal. So that means when you carry out the discrete Fourier transform, this will be the DC component. This will be the first harmonic. Now the first harmonic, F0, will be 1 over T0. So that's 1 over 50 millisecond, and this is 20 hertz. That means in this signal, continuous signal, I will be able to see the DC component here. Then the first harmonic 20 hertz, which is this one. Then the second harmonic will be twice F0. So I will be able to see the 40 hertz. And the third harmonic 3 F0. So I will be able to see those frequency 20, 40, 60, 80, and so forth. And we call this fundamental frequency also the frequency resolution of this data point. Now, if you want the frequency resolution to be better, then I have to make T0 larger than 50. Then this T has to be much longer. And there is a trade. I explained to you the time lagging, but also there is another trade for making T0 very large, because you may have 40 hertz present in these 2 seconds, let's say, but you don't know where did it start, where did it end. These data points just tell you there is a 20 hertz sinusoidal in the signal here. But did it start here or here? You don't know, because you made this long time interval. There is no perfect solution. There's always a trade. So after you did the sampling, you decide what's the sampling rate, and you decide what's the window or the interval of processing. What is omega 0? Well, the number of sample here, n equal whatever, 1,000 could be. So now omega 0 will be 2 pi over n. That's what we call the digital frequency. So how do we relate this omega 0 to the analog frequency that we are familiar with, either 20 hertz or in radians per second, like this one? So what's the relationship between these two? Well, if we start with a signal in the time domain, continuous, x of t is cosine omega 0 t, and then we want to convert it to a discrete x of n cosine omega 0. Now t will equal n capital T, where capital T is the sampling interval, which is the same as n divided by f of s. T, remember, is 1 over f of s. So then this will be n of s. So basically cosine omega 0 over f of s is n. And that's what we call omega 0. So the relationship omega 0 equal omega 0 over f of s, or the analog omega 0 equal the digital time the sampling rate. Just to give you a numerical example, if the fundamental is 2 pi over 1,000, n is 1,000, and I told you the sampling rate is 4,000, then omega 0 will be radians per second, or f0 will be just these 4 hertz, 4 cycle per second. So keep in mind this relationship, very important, because discrete Fourier transform take n of data point and give you another n of data point. It's your task to interpret. That's a DC. This is first harmonic omega 0. This is the second harmonic 2 omega 0 and n omega 0. Okay, now let's talk about the inverse discrete Fourier transform. Okay, the inverse discrete Fourier transform is basically, now you have all these data point in the frequency domain, you process them, you store them, you want to transmit them. Now you want to get back the signal x of n from this data point. Now we do the inverse discrete Fourier transform. And the definition is x of n equal 1 over n, the number of sample, k, go from 0 to n minus 1. So the meaning of this equation basically says the following. X of n here consists of a sum of sinusoidal function. Each sinusoidal has this strength. So just to visualize it, it's like this. First, you have the DC. That's when k equals 0. When k equals 1, you have this sinusoidal, and the strength of this one will be x1, plus when k now is 2, you have this sinusoidal, and with the strength x of 2. If n here is 1,000, then we will have 999. From 0 all the way to 999 sinusoidal, we add them up, and we will end up with the signal x of n, which is this. So this is the discrete Fourier transform. This is the inverse discrete Fourier transform. So let's demonstrate the discrete Fourier transform by images. Imagine our signal is this one. Now, you apply the discrete Fourier transform, which is this mathematical operation, the summation of all these data point samples, x of n, and you will get x of k. This x of k will tell you the spectrum of this signal x of n. If I plot the magnitude of x of k, it will look like this. When k is 0, that's the DC. That will be this height. When k is 1, that will be the strength of the first harmonic, which is this one. And the harmonic omega 0 is 2 pi over n, the number of samples. And this will be the second harmonic. If you want to get the signal x of n back again from the spectrum x of k, you do the inverse discrete Fourier transform, which is this one. And you will get back x of n. One thing to put in your mind is the following. See, this is a sum of x of k, which is a complex numbers, and this is also a complex number. ej, k, this one, I can express it as cosine. So the sum of all this complex number, where j, or some textbook, they call it I, just the square root of -1. So the sum of all these has to cancel all the j, so you end up with a real signal, x of n, because this is a real signal. It doesn't have complex. Well, this will dictate the following. Let me clean up first. That first point here is the DC, the strength of the DC component. Now this one, first harmonic, will be the conjugate of this one. Those are conjugate of each other. They equal in magnitude, the phase is opposite. Same thing, this component here will be the conjugate of this point here. So these two are conjugate of each other. What does that tell us is the following. This x of k is not unique. For example, let's say n 7 data points. So I have x of 0. Now this is the DC. This is the strength of the first harmonic. This is the strength of the second harmonic. And this is the strength of the third harmonic. Now what about this one? This is not a fourth harmonic. These two will be conjugate of each other. These two will be conjugate of each other. And these two will be conjugate of each other. So when you do the summation here, you will end up with this real signal. How do you determine how many harmonics you have? Is by these equations. If n is odd, like this case, then the harmonics you will have n minus 1 over 2, which is this one. 7 minus 1 over 2, that is 3. So I have only 3 harmonics. First, second, third harmonics. If n is even, then the number of harmonics will be n minus 2 over 2. For example, if n equals 6, then the number of harmonics will be 6 minus 2 over 2. That will be 2 harmonics. So let me just show you here. So for n equals 6, I will have the DC and all these components. So that's always n minus 1. This will be the DC. These two will be conjugate of each other. These two will be conjugate of each other. And that will be just a real number. So the rule is here. When n was 6, then x1 will be a conjugate of 6 minus 1, that's 5. And that's what we showed here. x1 is a conjugate with x5. x2 will be the conjugate of 6 minus 2, that's 4. And that's what we showed here. 2 and 4 are conjugate of each other. So let's take an example to show numerical calculation. This example, find the discrete Fourier transform of length 3. And this is the signal. And this is the plot of this signal. So the signal x of n equal 3, 2, 3. So n 3 elements. The digital frequency omega 0, or the fundamental frequency, is 2 pi over n. So you have no idea what was the sampling rate. In this example, it was not given to us, but in real life, when you are doing the application, you are the one who decided how many samples per second you will take. Okay, so we found omega 0. Now x of k is this. So that means x of k equal summation n goes from 0 to n minus 1. I have here n is 3, so 3 minus 1, that's 2, of the signal e minus jk omega 0. I found it to be 2 pi over 3 n. When n is 0, x 0, and here is 0, plus. When n is 1, that will be plus. When n is 2, that's the last thing, time 2, equal. Now I plug value for x0, x1, x2 from here, from this input. So x0 is 3, that's this one. And this e to the power of 0 is 1, plus x1 here is 2, plus x2 here is 3. For k, remember, k equals 0, 1, 2. The last one is always n minus 1. That's how many data you have. Now, if I want to find the DC, x0, all I have to do is just plug for k 0 in this equation. So that will be 3 plus 2 e to the power of 0 is 1 plus 3. Again, when I plug for k0, e to the power of 0 is 1. So that will be 8. Now, if I want to find the first harmonic, x1, then wherever I see k here, again, I plug 1. So that will be 3 plus, and if you use your calculator, you should get the following. Minus 0.5 plus 3. And again, if you use your calculator, this will be. Now, if you add the reals and the imaginary here, this will finally comes to be 0.5 plus j. Same thing. If I want to calculate x of 2, because k can be up to 2, I will go to this equation here and plug for k 2. So this will be 3 plus 2. And if you use your calculator, I can assure you this will came 0.5 minus j 0.866, which is the conjugate of these. Since n equal 3, then you will have a DC and you will have first harmonic. x2 will be just the conjugate of this one. So x2 will be just the conjugate of x1. So you don't even need to calculate it. From here, I can get this value. So that is the strength of the DC, and this is the strength of your harmonic, which is 2 pi over 3. Now, if I want to know this 2 pi over 3, which is radians per 3 samples, what does it mean in hertz? An actual physical signal in the continuous, in the analog. Then this will be omega 0 equal the digital omega time the sampling rate. 2 pi over 3. Let's say the sampling rate was 12. So then this will be just 2 pi 4. So the fundamental frequency is 4 hertz. or 4 cycles per second. So x of k So the discrete Fourier transform took you from here to here. Let's now demonstrate the inverse discrete Fourier transform. So in this example, we found the discrete Fourier transform to be this one. Now let's say we did some processing by removing the DC. So we took x of k here to a filter, let's say, that remove a DC, and we got y of k. So y of k consists only of the following. The DC is eliminated, which is this one, so that's 0, 0.5 plus. And now I want to find what is the signal y of n. So now I have to do the inverse discrete Fourier transform, which is defined by this equation here. So y of n equal 1 over the number of samples. I have 3 of them. Summation from k equals 0. Now my variable is k. n minus 1, that will give me 2. Y of k, those are the frequency content of the signal. And when k equals 0, this will be 1 over 3. For y of 0 is 0. ej, k is 0. Plus, when k is 1, then it will be y of 1. When k is 2, that will be, and this is y1 is this one here. Omega 0 is 2 pi over 3. y2 ej. And remember, there are only 3 samples, so n will be 0, 1, 2. Again, this is just n minus 1, the number of samples. Now, if I want to find y0, y1, and y2, so y0 will be, wherever you see n here, plug for 0. So that would be 1/3. And when you plug for n here 0, that will be 1. E to the power of 0 is 1 plus, again, plug for n 0, that will be just 1. And this will be 0.5 plus 0.5 is 1. This will cancel this, so 1/3. If I calculate y1, I go back here again and plug for n1. So this will be 1/3. If you use your calculator, you will get this to be minus 2 over 3. And the same thing to find y of 2. Just plug for n here, 2. And if you use your calculator, you should get 1 over 3. That's the answer we got here. So y of n the original signal before eliminating the DC was x of n 3, 2, 3. And when you remove the DC here, we found x 0 equal 8 in the discrete Fourier transform domain. So how much DC did we remove? It is always x0 divided by n. In this case, n is 3, so it is 8 over 3. So basically, subtract from this signal 8 over 3. So 3 minus 8 over 3, that is 9 minus 8, that's 1/3. That's this here. Now, how did we get this one? We have here 2. So 2 minus 8 over 3. That's 6 minus 8 over 3. That's minus 2 over 3. That's what we got. So you remove the DC component, then this signal, which was this 3, 2, 3, now it became 1/3 minus 2/3 and 1/3. After removing from here that much DC. Okay, let us go back to this example where we find the discrete Fourier transform. So we started with x of n, which is this one. But first, let me clean up just to highlight some other point. Okay, so in this problem, we had x of n, and we used the discrete Fourier transform to find x of k. And we found x of k to be this one. So now, if I want to express these instead of rectangular form to a polar form, then that would be 8. That's the magnitude. The phase is 0. So I'm going to say EJ0. Take the magnitude and the angle. Just to remind you, the magnitude will be the square root of 0.5 square plus 0.866 square. And if you do this, you will get 1. And the phase will be tan inverse the imaginary 0.866 divided by the real 0.5. And if you do this, you will get pi over 3. And now we will take also this one. It will be just a conjugate of this one. So the magnitude will be the same, E minus J pi over 3. Now, if I plot the magnitude, it will be just the 8, which is this one here, the 1, which is this, and the 1, which is this. And if you plot the phase, which is 0, that would be here is 0, and the pi over 3, which is this one, and the minus pi over 3, which is this one. Now, I also can rewrite these as follows. I will combine these two terms first, so the 3 will be out here. And then I will take E minus J 2 pi over 3 K as a common factor from this term and from this term. So then I will have here EJ 2 pi, and from this term I will have E minus J plus this term. Now I can divide this by 2 to make it a cosine and multiply here by 2. So then this will be what I did is this one, I brought it here. Now I will combine these two terms, this term and this term, by taking a common factor, which is this. So then this will be 2. What's left from here is 3 cosine. What's left from here is just 1, or is the same as. So that's x of k. But this is valid only for k equal again 0, 1, and 2, where this is just n minus 1, 3 minus 1 is 2. So that's another way of expressing x of k in a closed form. You express it in this form is good. You express it in this form, that's also fine. Now just to link the discrete Fourier transform to the discrete time Fourier transform, which is this equation, if I try to find the discrete time Fourier transform for this signal x of n, basically finding x of omega, I carry out this definition and I will get this one here. So let me write it here, x of omega, ej omega. Now, if I compare this one to this one, you will find here I have omega. Here I have 2 pi over 3k, or which is omega 0k. So the difference between this one and this one, these I discretize the frequency. If I plot this signal, that will be the solid plot. Now, when you do the discrete Fourier transform, you get this one, which is basically you sample omega with a frequency resolution omega 0, which is 2 pi over 3. So now I get only these samples. This is the sample x of 0, that's here, which is 8. This is x of 1, which is this component, or this component. And this is x of 2, which is this component, or this component. Now, what if I want more samples? These 3 samples is not enough, because I'm missing that peak, I am missing what's happening here. So I need to take more samples. Yes, these 3 samples were enough to even give me the whole continuous spectrum if I calculate x of omega. But what if I need, instead of 3 samples, 6 samples? Well, if I still have the original signal, I take more samples. So instead of 3, 6 samples to get 3 more samples. But if I don't have the original signals anymore, and I only have these 3 samples based on the sampling theorem, then all I have to do, if I want the frequency resolution here, omega 0, to be much better than 2 pi over 3, so much smaller, like 2 pi over 6, that means n should be 6. So where am I going to get 6 data points? We augment this x of n by 3 zeros. So now it is 3, 2, 3, 0, 0, 0. Now n equals 6, and the frequency resolution omega 0 will be 2 pi over 6. X of k here will have now, instead of 3, it will have 6 data points. So I'm going to have another sample here, another samples here, and another samples here, just by augment these by 3 zeros. Okay, let's demonstrate the impact of zero padding to improve the frequency resolution in the discrete Fourier transform by looking at this example. This example is similar to the example we did before, where xn equal 3, 2, 3. And that's what we did in the previous example. And in that case, the frequency resolution was 2 pi divided by n, which is 3. Now, if I want to improve the frequency resolution so I can see more samples, instead of seeing these only 3 samples, 1, 2, 3, now I need to see more samples. So I need to see those 3 extra. Then one solution is to pad these by 3 zeros. So now it will be 3, 2, 3, 0, 0, 0. And now the frequency resolution will be 2 pi over 6. And now we will carry out the discrete Fourier transform to find x of k, which is, again, this is the definition, n minus 1, which is 5, because n here is 6. Okay, so this will be, when n is 0, x of 0 is 3. When n is 1, x of 1 is 2. When n is 2, x of 2 is 3. When n is 3, x of 3 is 0. When n is 4, x of 4 is 0. When n is 5, x of 5 is 0. So this is really plus 0, plus 0, plus 0. So x of k will be, this will be e to the power of 0 is 1. So that will be 3 plus, plug for omega, this value. Again, this omega 2 pi over 6 times 2, that will be 4 pi over 6. Now, if I want to find the DC, I plug for k0. So x DC, that will be 3 plus 2 plus 3. If I want to find the strength of the first harmonic, that will be 3 plus. And if you use your calculator or convert these to rectangular form, add and convert them back to a polar form, you should get the following. Now, how many harmonics you will have? Well, according to this definition in previous slide, for k equal 1, 2, all the way to n minus 1 over 2, when n is odd, or n minus 2 divided by 2 when n even. In our case, n is even. So I know that k will be 1, 2, 6 minus 2 divided by 2. That's 2. So I will have first and second harmonic. So that means I already calculated x of 1. Now I need to calculate x of 2 and x of 3. I don't need to calculate x of 4 and x of 5. Let me write them here just to show you. So that's the DC, x of 0, x of 1. So I have n6. I will get here 6 data point. So this will be the conjugate of this one. So if you plug here k1 and here you plug 6 minus 1, that's 5. So x1 and x5 conjugate, x2 and x4 are conjugate, and x3 are real, no complex. Otherwise, it has to have its conjugate. So I already calculated x0, x1. Let's calculate x2 and 3. 4, 5, I don't have to calculate them because I can find their value from x1 and x2. So x2, again, plug for k2 here and here, and you should get and if you use your calculator, you will get, and x3, plug for k3 here and here. And if you use your calculator, it will be 4EJ0, which is 4. Now x4 will be the conjugate of x2. So that will be 1e minus j pi over 3, the conjugate of this one. x5 will be the conjugate of x1. So that will be 5e conjugate of this one. And they are summarized in this table here. And if you plot them, they will be this one. And that will be the phase here. So from this example, we showed just by add zeros to the original signal, you improve the frequency resolution by increasing n from 3 to 6. So now you will be able to see all this frequency resolution. And to show you the importance of enhancing the frequency resolution, let me show you these examples. We have a signal x of t, this DC, with 3 sinusoidal, sampled at the Nyquist rate 6 samples per second, and the signal is sampled for 1 second. What are the discrete Fourier transform component x of k? Will you be able to see the 1.5 hertz, this frequency? In real life, you probably pick up this signal, you don't even know the mathematical expression, and that signal could look something like this. Now they said the sampling rate is 6 samples per second. Also, they sampled it for 1 second. So probably they took something like this, 1 second. And they took these samples, 6 samples. Now the question is, with these 6 samples, x of n, 6 samples, x of 0, x of 1, all the way to x of 5. Now, if you apply the discrete Fourier transform, will I be able to see all these frequency components, like the 1 hertz, the 1.5 hertz, the 3 hertz, and the DC? Well, the digital frequency resolution. Omega 0 is 2 pi divided by the number of samples, so that's 2 pi, divided by 6, so that's pi over 3. If I want to see what is the frequency resolution in the analog, it will be f0 times the sampling rate. Well, if I rewrite this is 2 pi 1 over 6. So this is f0. So that will be 1 over 6 multiplied by the sampling rate 6. So that is 1 hertz. Or you can also find it from here. Since we are specifying t0 to be 1 second, then f0 will be 1 over 1 is 1 hertz. That means I will see the DC. The fundamental frequency is 1 hertz. So I will see the first harmonic, the second harmonic, and the third harmonic. So I will see 1 hertz, 2 hertz, 3 hertz. So I will not be able to see the 1.5 here. So in order to see the 1.5, the frequency resolution f of 0 here should be 0.5 Hertz. So the first harmonic will be 0.5. The second harmonic will be 2 times 0.5, which is 1. So I will be able to see this one, 1 Hertz. Then the third harmonic will be 1.5. So I will be able to see this one. That means instead of sampling only 1 second, now I need to sample 2 seconds. So now I need T0 to be 2. So F0 then will be 1 over 2 is 0.5. Okay, let me use MATLAB without mathematical calculation to demonstrate the discrete Fourier transform and the importance of sampling rate and the window or the time interval of the signal we will be sampling and processing to reveal the true information about the signal. So assume your sensor is picking up this continuous signal and you decided to use sampling rate 7 and the time interval or the window to be 1 second. So you took these 7 samples all the way here to 1 second and you received these samples here. Now, if you use MATLAB, you can calculate the discrete Fourier transform using this function FFT. And you pass to it the samples here. This function will return the discrete Fourier transform x of k, which is the spectrum of the signal, 7 data point. If you calculate the magnitude, this will be the 7 data point. The phase will be this one. So now let's see if we can find from these samples the representation of this signal either in the discrete form x of n or in the continuous form x of t. So the first step is to calculate the digital frequency omega 0. Well, omega 0 equal, where n is the number of sample. So we calculate this. Now we need to calculate the DC present in the signal. This one in the discrete signal or this one in the continuous representation. Well, the DC equal x of 0 over n, where x of 0, that's the magnitude, and n is the number of samples. So that will be, that's this one. The next step is to calculate the amplitude of the first harmonic. Well, this is the first harmonic, and the magnitude is 7. Now here we multiply by 2 because harmonics we have actually 2 components of it. This one and its conjugate, this one. Same thing. This second harmonic and this is the conjugate. And this is the third harmonic and this is the conjugate. That's why we have to multiply by 2. And this is the amplitude 2 here. And now we need to calculate the phase shift, theta 1. And this will be the phase of this first harmonic, which is this one, 0. So now, so far, we got the DC and we got the first harmonic, theta 1 to be 0. Now, we calculated the digital frequency, omega 0. So what is the analog frequency? This one, omega 0. This will be the sampling rate f of s is 7. And if you calculate this will be 1 Hertz. So that will be 2 pi 1 Hertz. Let's do one more calculation of the second harmonic, the discrete or the continuous. Well, this is the second harmonic. The magnitude is 3.5. So A2 then will be, the magnitude is 3.5. So that A2 is 1. And if I need to calculate the phase, theta 2 will be tan inverse of the imaginary divided by the real. And this will be 3 pi over 4 minus. That will be this one, or it's the same thing as this one. Remember, pi here is the radians, 3.14. And the frequency of the second harmonic will be 2 omega 0, or in the continuous 2 omega 0, that will be 2 pi times 2. And we can do the same thing for the third harmonic. Now, if I plot this signal here, I will get exactly this continuous signal. So from 7 data points, we were able to get the actual continuous signal or the discrete signal. So now let's take an example to show the impact of sampling interval. So let's say you let the sensor have the same setting, basically sampling rate 7 samples per second, and you sampled a segment of length 1 second to figure out what was the continuous signal. Now the signal here is a little bit different than the previous one, but you didn't modify your sensors and you took samples for 1 second. So these are the samples you received, are these 7 samples. You apply the discrete Fourier transform to these samples, you got x of k here. This is the absolute value and this is the phase. If you calculate A0, A1, A2, same way we did earlier, this is the signal you will get. If you plot this signal, that's what you will get here. It's totally different than this signal because you only sampled for 1 second, you missed that information about the signal. So the signal looks like this. So then what's the solution? Well, the solution is the following. When you look at this signal, you can see it repeats itself every 2 seconds. So this point here, it repeats itself every 2 seconds. So my sampling segment should be 2 seconds. So now if I sample the signal for 2 seconds, I will get 14 samples. So now n is 14 and the frequency resolution is 1 over T0. So that is 1 over 2 seconds. That is 0.5 hertz. So I will be able to see a signal that is either half hertz or 1.5 hertz or 2.5 hertz. And when you look at these 14 samples, these are the 14 samples. You apply the fast Fourier transform, which is the discrete Fourier transform. That's x of k. This is the magnitude, and this is the phase. And you calculate A0 the same way we did before, A1, A2, and A3, and theta 1, theta 2, and you will get this equation. Now, if I plot this equation, I will get exactly this continuous signal. See, because I made my sampling interval 2 seconds, so the frequency resolution is 0.5 hertz, I was able to detect this 2.5 hertz sinusoidal signal correctly. Before that 2.5 hertz spectral spreaded between a 2 hertz, and some of it went to the 1 hertz and some of it went to the 3 hertz, and which is not the correct signal. Okay, these end the topics of this video, and next video we will talk about how do we use the discrete Fourier transform for signal processing, designing filter system that will take a discrete signal and give us a desired signal. Thank you again and see you soon.